do y'all have any questions, issues, problems, concerns? The good news is we'll be able to meet, knock on wood, today and Wednesday, so y'all won't lose any material. I may be even slower getting great things graded, but part of the time when I'm in the clinic waiting for them to give me this, give me that, stick me with this, give me whatever, I'll be grading papers. I'm collecting them. I collected quite a few over the weekend. I'll try to collect a few more during my office hours when I'm available to do so this week. So I'll go in there with a stack of papers I can be grading. So Kyle, the odds are that's when I'll be grading your paper. So you better hope I'm feeling good. Okay, never mind. I'm just kidding. But anyway, that's it. Do y'all have any questions, issues, problems, concerns? All right, where we left off last time, we're in Chapter 11, Vectors in the Geometry of Space. We're in Section 11.3, which is the dot product of two vectors. And we've introduced that last time. And now we're looking at this slide here. Let me get it, PowerPoint open to the current slide. And this figure here, the theorem we just did, let me go back and just review that theorem. If theta is the angle between two non-zero vectors u and v, and that the theta is somewhere between 0 and pi, in other words, between no angle between them and 180 out, okay? We're not going anything past that, okay? Then here's another definition or use of the dot product. The cosine of the angle in between those two vectors is the quotient of the dot product of those two vectors divided by the magnitude of each of those vectors. That's the cosine of the angle in between. And here comes Miguel Jesus. Let me get him here. Okay, we're just missing two people, Houston and Jemanuel. So hopefully we'll get one or both of them in soon. Let me make sure that I haven't missed them and that they're not out there waiting. I think not, because that would have shown up when I let Miguel Jesus in. Okay. So, with that in mind, let's look at some applications of those angles. Let's first look, if I could get the slide to proceed here. This figure, they say, shows two possible orientations of two vectors. Looks like to me there's more than two, okay? But here's vector v here. Now the maximum, remember that angle theta could be, would be pi, or 180 degrees. In that case, the cosine between those two angles is -1, okay? We know that. The cosine of pi is -1. The cosine of an angle, an obtuse angle, in between pi halves and pi, or 90 degrees and 180, that's going to be, cosine is negative in this quadrant, second quadrant, so that's going to be between -1 and 0. It was -1 when it's straight out. It will be 0 when it's directly above head, okay? So I guess they're talking about this orientation and that orientation, okay? When they're perpendicular to each other, get this now, any two vectors perpendicular to each other, the dot product is 0. The cosine of the angle between them is 0. That puts the angle to be pi halves, which is right where we started from. If they're perpendicular, the angles pi halves are 90 degrees, and if they are, the dot product is 0, because the cosine of 90 degrees, or pi halves, is 0. If it's an acute angle, then the cosine is positive, and it will be between 0 and 1, okay? Because cosine at 0 is 1, and any acute angle will be between 1 and 0, 0 and 1, okay? So I guess that's what they meant, the two possible orientation, obtuse angle or acute angle, okay? Obtuse angle, the dot product will be between, okay, that's not quite true. The cosine of the angle will be between 0 and -1, and acute angle would be between 0 and positive 1. Okay, and that's the full range of your cosine function between 0 and between -1 and 1. Okay. Any questions on that? Again, I didn't think everything they say in this slide is true. I just couldn't, it's sort of hard to figure out what their point was, but that is the point. Okay. Now, from that theorem, you can see that two non-zero vectors, if they meet at a right angle, if and only if their dot product is 0. So that means if they're perpendicular, the dot product is 0. If the dot product is 0, they've got to be perpendicular. Now here's another word for it. They are orthogonal. Same definition, same meaning as perpendicular. Only when we're talking about vectors, oh, here comes Houston. Now we got 7 out of 8. Way to go. If we can just get Jemanuel here, we'll have perfect attendance today. Hopefully he'll be coming in. Okay. Houston, I went into a long monologue before you got here, but I forgot to turn on the the screencast-o-matic, so you won't be able to hear it. I'll summarize it here. My office hours this week are going to be pretty shaky. This afternoon from 4 to 6, I may have some phone calls to make for a couple of issues. Hopefully I can focus mostly on my job and not the other issues that are flying around me right now. Tomorrow, Tuesday, from 1 to 3, as the only office hours to speak of I've got tomorrow, I know that the chaplain at Episcopal Place is going to be calling about a memorial service of a friend of mine who died last week, so I've got to be dealing with her. I'm the contact person for just about everything to do with Judy's death. She had a pulmonary embolism or something like that. She died at 76 last Thursday. She was collapsed on Tuesday and was in either the emergency room or intensive care for the rest of the time she was alive. So I'm dealing with that because I'm the contact person for her belongings, her artwork, it may even turn into her money. There's not going to be much there. Her arrangements, fortunately she left her body to UAB, so UAB has got it, and they're just going to send me some paperwork. That was a phone call I had to make this morning, and we got that straightened out. So I've got some paperwork to do there, but they'll send it in the mail. That won't take much time to get that done. Okay, but office hours this afternoon, 4 to 6, hopefully will be pretty much free for me to work on my job. Tomorrow, 1 to 3, part of that time I'll be tied up with the chaplain at Episcopal Place, but hopefully that won't be too long. So I will have office hours some tomorrow. Wednesday, 8 to 12, hopefully nothing too much interfering there, so I will have office hours then. Wednesday afternoon, though, I've got to go with a guy from the church who's really good with photography and computer stuff, and he's going to go and photograph all of her artwork and some of her furniture and stuff like that, so we can determine if there's anyone who wants or needs anything that she had. We'll distribute that, because she was in a HUD assisted living, and HUD requires that once a person dies, you have to clear the apartment in 2 weeks. You have 14 days, and that's counting right now. She died on Thursday, so we've got a very small window to have to deal with everything. So that's why Wednesday afternoon basically shot. And then on top of all that, I may be having a treatment Thursday and Friday. I thought it was only going to be 1 day. They're going to extend it into 2 days because my counts are so high. So that's probably going to take me out of pocket all day Thursday, all day Friday. So however the schedule has it, they haven't gotten back to me on when they were able to schedule me. If it's not next week, it'll probably be the following week. So so this may all be postponed for a week, and that would give me more time to work on the other thing and get more things done. But anyway, that's where we are. Thursday and Friday may be completely gone, wasted. You know, I'm not here. Okay. I've talked with my boss at Lawson. He understands it all and which wishes me well. He's not at all concerned with things. But the good news for this class, it won't affect you more than maybe the phone ringing, which it did in this morning's class, which was a pain in the neck. But the chaplain called and someone else called, and so I sort of have to deal with that when they come, because I'm only available during their working days, so I've got to accommodate that. So if I do have a phone call, that's why it is. If you can't get me during office hours, that's probably why. So anyway, enough of that. Did you have any questions, issue, concern before we get back to calculus? Okay. Sorry about taking so much time again, but Jesus, you got to hear it too. Okay. Now, like I said, if the two angles are at right angles with each other, the dot product's got to be 0. If the dot product is 0, they got to be at right angles. They're said to be orthogonal. So here's the definition of orthogonal vectors. If the two vectors u and v are orthogonal when their dot product is 0. That's it. I mean, that's how you determine if two vectors are orthogonal. Dot product is so easy to do. Okay. So let's see if I can get my screen to advance, and we're over on page 772. About the middle of the page is oh, and by the way, they say here here's a few other terms. Of course, I've used the term perpendicular. They use the term orthogonal. Also, when we're talking about vectors, we'll talk about them being normal to one another, which also means perpendicular or orthogonal. Why so many words for the same meaning? I don't know, but they all mean essentially the same things. Okay. It's common, however, to say two vectors are orthogonal, two lines or planes are perpendicular, and a vector is normal to a line or a plane. So that's sort of the minor distinction between the three. Two vectors are orthogonal. Two lines or planes would be perpendicular, and a vector reacting with a plane or a line would then be said to be normal to the line or the plane. So that's what they mean. Now, another weird corollary, you might say, or result of that definition, this definition, is that then, notice they just said two vectors. They didn't say, like they did earlier, two non-zero vectors. In this definition, all they say, if the vectors u and v are orthogonal when u dot v is 0. Well, guess what, folks? If either u or v is a 0 vector, then the dot product's always 0. And then the weirdness of it, you say that the 0 vector is normal or orthogonal to every vector. Okay, which is a rather odd thing because a 0 vector has no magnitude and no direction. So how can it be orthogonal to anything? But by this definition, it is. Okay, so stand by for that. So let's move on to example 2, middle of page 772. Example 2, and this is also found at larsoncalculus.com for an interactive version of this type of an example. So here we have 4 vectors in space, 3 space, R3. 3 minus 1, 2, minus 4, 0, 2, 1, negative 1, negative 2, and 2, 0, minus 1. And what they say is find the angle between each of these pairs of vectors. First, between u and v. Okay? And that is not a particularly difficult thing to do if you remember what our formula was. And if I can get the pen to show up, there it is. That let's call the angle between these two, what you want to call it, theta 1. You okay with that? So the cosine of theta 1 is equal to, okay, remember what it was? U dot V, both of those are vectors. That's a dot product, which is going to produce a scalar answer, a numerical answer, not a vector, divided by magnitude of U times the magnitude of V. Okay, so maybe a good idea for us to do is first do those magnitudes so we don't have those hanging over our heads. So let's do that first. I don't know where to do it. Let's see if I can squeeze it in up here. The magnitude of vector U is the square root. Can anyone tell me what it would be? 3 squared plus a -1 squared plus 2 squared. That's what your magnitude is. Always positive, always non-zero if it's not the zero vector. So this would be the square root of 9 plus 1 would be 10 plus 4 square root of 14. So there's the magnitude of U. Magnitude of V. I wrote a U again, didn't I? If that would just go away. Magnitude of V would be the square root of, can I go on and just do them? 16 plus 4, that's the square root of 20. Was that too quick? 4 squared is 16 plus 2 squared is 4, that's 20. And that, by the way, you can factor out a 4, which is a perfect square. The square of 4 is 2, the square root of 4 is 2, so that would be 2 times root 5, because you'd have 5 left over if you factored out the 4. Okay, let's do the magnitude of W. I forgot to put my arrow over the V. Okay, now what would that be? The square root of 1 plus 1 plus 4. That would be square root of 6. Okay, magnitude of Z. Would be the square root of 4 plus 1 is 5. Okay, so there's our magnitude, so we don't have to worry about those anymore. Okay, now let's do the dot product of U and V. Does anyone remember how you do the dot product? If I could get my pen to show up, where is it? Where are you, pen? There you are. Okay. The dot product is the product of the corresponding terms. 3 times a -4 would be a -12 plus -1 times 0 is 0 plus 2. I mean 4. 2 times 2 is 4. Okay, so that's -8 over the product of U and V, and that would be V was 2 root 5 times root 14, and 5 times 14 would be 70, so 2 times the square root of 70. Now I'm trying to think if there are any common factors between that. There are not, I don't believe, okay, because it's 2 times 7 times 5. Okay, so that would be that. Well, this would then be, come on pen, show up somewhere. This pen gets lost. There we go, somewhere up there. Nope, there we are. This would be -8 over 2 root 70. Okay, well 2 will go in the 8 4 times, so that'd be -4 over root 70. Okay, now all that does is give you the cosine of the angle. Okay, now here's a place to be a little careful. Okay, remember the cosine of an angle can only be between -1 and +1. Well, certainly this is negative. The square root of 70 is something greater than 8, right? Because 8 squared is 64, so this is something a little bit less than -1/2, or greater than -1/2. So yeah, that's within the range. So I've got to pull out my handy dandy calculator to make this work, which is my phone. And let me turn it on. I've got to charge it in a little bit. Okay, and get my calculator mode up here. I've got to deal with square roots and cosines, so I'll turn it sideways to get it into scientific notation. And it just came back. Okay, so we'll do 4, and then I have to change the sign of that, divided by 70, and I'll take the square root of that. That's equal, and that's a negative number, and it's a little bit greater than 0.5 like we said, so that's making sense. And now I need to do the inverse cosine of that. Okay, y'all remember that from trig? You better. The inverse cosine of that number. So I've got to go on my calculator and go to second mode, and that changes the sine, the cosine, and the tangent to inverse sine, cosine, and tangent. So take a I'm in radian mode, as degree mode. I've got to change to radians. Now I will take the inverse cosine of that thing and get 2.06, or let's just call it 2.1 radians. So find the angle between that, theta 1 would be approximately 2.1 radians. Okay, let's think about that. Does that make sense? 1 radian would be something about 56 degrees. 2 radians would be 58 degrees or something like that, just under 60 degrees. 2 radians would be just a little bit under 120 degrees, so 2.1 radians is going to be pretty close to 120 degrees. Second quadrant, negative, sure enough, that makes sense. So that's the angle between U and V. Let's see how the book did. They put 2.069 radians, which is fine. That's what I got too. I just don't see how they get 4 significant digits out of something that you only had 1 significant digit in any one piece of it. So that's their problem to deal with. The B part, maybe I should have called this theta A. That would have made more sense. Let's do theta B now. The cosine of theta B. Well, that's the angle between U and W. Well, U and W, I'm going to erase some of this because it's getting so crowded there. So let's come down here and erase little stray marks like that. I'll not mess with those. Let's erase these here. Okay. All right, I'll leave the rest of those up there. Get my pen back. Okay. Theta B would be then U dot W divided by the magnitude of U times the magnitude of W. All of those are scalars. Magnitudes are scalars, dot products are scalars. Okay, U dot V, that's the one we're doing, right? Yeah. 3 times a 1 would be 3 plus, whoa, here comes your manual. Ding, ding, ding. We're perfect attendance today. If I could get my finger on the right thing. Way to go, team. Perfect attendance. All 8 of you here. I had all 4 of my Cal 2 students this morning. Perfect attendance day so far. Way to go. Okay. And Emmanuel, I don't know if you're in yet, but if you are, this is it, folks. I won't say this again. The my office hours this week are kind of trashed. Okay, this morning I had. Now I think I hear my phone ring. No, I don't. Okay. This morning, part of my office hours were spent dealing with a couple of issues. Well, one issue in particular, the death of a really close friend of mine that I'm the contact person, who was named. No family in the state, no family, no close family, period. Um, so I've had to be dealing with chaplains and pastors and UAB and uh, artwork and belongings and what to do with stuff, and it has been nuts. So part of my office hours this morning were eaten up doing that. Not all of them, but part of them. This afternoon, 4 to 6, hopefully I won't have that much to do. I know I've got to send at least one email, but more may have exploded since then to deal with that. And then tomorrow's office hours between 1 and 3 in the afternoon. Part of that, I've got a phone call with the chaplain at Episcopal Place, so I'll be out of pocket then, but hopefully the rest of the time I'll be in pocket. And then Wednesday morning from 8 to 10, about like this morning, hopefully most of it I can spend on work stuff, but I may have some things that come up Wednesday morning. Wednesday afternoon then, completely shot, because I've got to meet with a guy from church who's really good with photography and computer stuff, and he's going to be taking pictures of my friend's artwork and furniture and stuff like this, so we can get it just out to people to see if anyone wants anything before it all gets disposed of. So that's that. Thursday and Friday, there is a real good chance I've got to go in for treatments. Of course, that would happen the week all this is going on. I'll find out hopefully later today, no later than tomorrow, when those treatments have been scheduled. But they were trying to get them Thursday and Friday of this week. I'm surprised at that, because I thought I could have them all in one day on Friday and wouldn't lose any class days. Now it doesn't seem like that's going to happen. So I will be there. Well, 1 week coming up soon, possibly this week, I will be out of pocket all day Thursday and all day Friday. So I'll lose all my Thursday classes, possibly. I may get home in time to do that late class, or at least part of the late class, but sometimes after a treatment I am so zoned out because of the Benadryl, I may not be able to handle the class, but I'll try to do it. That's the only bad part. There's nothing bad about the treatment. The bad part is the pre-treatment stuff, especially the Benadryl. It makes me very, very sleepy. And then Friday, if I have treatment, that day will be completely gone, because it's going to be 90% of the treatment, and that will take from 7:30 in the morning probably into the afternoon, way past my 8 to 12 office hours. Okay, so I may be out of pocket. Definitely be out of pocket Wednesday afternoon, 4 to 6. We'll be out of pocket a little bit tomorrow, 1 to 3, and maybe completely out of pocket Thursday and Friday. We'll see. Okay, I'll let you know on Wednesday what we know. I've got to know things by then, or at least most of it. Okay, now where we're in chapter 11, vectors and geometry of space. 11.3, the dot product of two vectors. We're on page 772 doing example 2, which you see on the board, and that's finding the angle between two vectors. We had done the angle between u and v, found it to be 2.1 radians. We're now doing the angle between u and w, and we're just doing the dot product here. That's what was in the process of doing when you came in. So let's continue from there. The dot product is the scalar product between the corresponding components. 3 times 1 is 3, so that's why I've written down the 3 there. Plus -1 times -1 is +1. Okay? And 2 times -2 is -4. Whoops! Whoops! It doesn't matter what this denominator is. What is that numerator? 4 minus 4 is 0. So what's the angle theta B? In radians, pi halves. If you want to express it as a decimal number, you could just take pi 3.1416, divide it by 2, and you get 1.5718 or something like that. Okay, but there is your angle B. Okay, theta B. The C part here says find the angle between V and Z, so cosine of theta C, we'll call that, is the dot product between V and C. Okay, I'll go and write it down. V dotted with Z divided by magnitude of V times the magnitude of Z. Okay, dot product between V and Z. -4 times 2 would be -8 plus 0 minus 2. Okay, so that's a -10 over, and we had done the magnitude of V and Z. Up here, magnitude of V was 2√5. We did that earlier. And the magnitude of Z was √5. Okay, so √5 times √5 is going to be 5. 2 times 5 is 10, so this is -10 over 10. That's a -1, and what's angle would give you a cosine of -1. Theta C would have to be pi. Remember, cosine starts at +1, goes to 0, and then at pi it goes to -1. So that's going to be theta C would equal pi. Okay, let's see what they got. Yep, theta C was pi, theta B was pi halves, and we already did theta A. All right, that's how we did it. Want to see how they did it? Probably fairly similar, but they may have had some slightly different approaches. Solution here, the cosine of A here between U and V would be U dot V over magnitude of U times magnitude of V. Without telling you anything, they just do it. Again, that would be 3 times the -4, that's a -12, plus 0 plus 4. Wait, yeah. So that would be -12 plus 4 is, yep, that's what they got here. And then over the radical, 9 plus 1 is 10, plus 4 is 14, and 16 plus 4 is 20. So that's where they got these. That would give you a -8 from up here, a 2 that you pulled out of here times 14. That would be 2 times √70. So -4 over √70. They canceled the 2 into -8 and got -4. So that's why they lost the denominator there. And then you just take that and do the inverse cosine of this number right here, whatever it turns out to be, and be sure you're in radian mode. That gives you 2.069 radians, which I'm very happy just to call 2.1, or no better than 2.07. Can't convince me you can get 4 significant digits out of single digits. Okay, it's just not physically done. But because also the dot product is negative, you know the theta has to be in the second quadrant and surely 2.09069 radians is in the second quadrant. All right. The second one, cosine of theta, is u dot w divided by magnitude of w, u times the magnitude of w. Okay. Well, u dot w was 3 plus 1 minus 4, which happens to add up to 0. So it doesn't matter what the denominator is, the numerator is 0, so this fraction is 0. And they carried it out. Why, I don't know, but they did perfectly fine to do so. You could have simplified that some, but why mess with it? That's equal to 0. Well, if the cosine of theta is 0, you know theta has to be pi halves because they are orthogonal. Okay, orthogonal, two vectors are orthogonal is the same meaning as two lines being perpendicular, or a line in a plane being perpendicular, or a vector being normal to a plane, say, or to a line. And so all three of those terms mean the same. Theta equal pi halves. All right. The C part then, cosine theta would be the dot product of V dot Z over the magnitude of V times the magnitude of Z. And that was minus 8 minus 2. We got that also, divided by square root of 20 times square root of 5, which is square root of 100, which is 10. So that's minus 10 over 10, which is minus 1. And the only place where cosine has a cosine of some angle is equal to minus 1, the cosine would have to be pi, because you're only defined between 0 and pi. That would be at pi. So consequently, theta is equal to pi. Notice that V and Z are parallel with, and I don't think you noticed that, but let's go back and show that. Here's V, negative 402. Here is Z. The quotient of negative 4 and 2 is a negative 2. 0 and 0, yes. 0 and 0 would be anything, and the quotient of that would be a negative 2 as well. So you see they only differ by a factor of minus 2. Minus 2 times 2 is minus 4, minus 2 times 0 is 0, minus 2 times minus 1 is positive 2. So yes, they are collinear. One's going one way, one's going the other, but they are collinear vectors. Whoops, went too far. So therefore, those vectors are parallel to one another, with V being minus 2 times Z. Exactly like we said. Okay, now, when the angle between two vectors is known, and sometimes it is, rewriting that theorem comes out this way. The dot product between U and V, remember we said it before, cosine is the dot product divided by the magnitudes. Well, here's a new way to write it. Multiply both sides by the product of the magnitudes, and you have U dot V is magnitude of U times magnitude of V times the cosine of the angle in between. Guess what? There's another definition of the dot product. Now, this would be if you didn't know precisely what the components of either U or V is, but you did know the angle between the two, which I don't know, excuse me, in a physical sense when that would ever be the case, but I'm sure they'll make up one mathematically where it would be the case. Then you can calculate the dot product in this way. Okay, as I've said several times now today, I'm very anemic, and after a while I just run out of gas. So I'm drinking caffeine and sugar trying to keep going. So hang on, sorry about this, but I just get so tired my head aches. So let me get this. hopefully that will get me going for a little bit. No guarantee though. So there's your alternative way to calculate a dot product. So I bet you example 3 is going to use that. Oh, but they don't do example 3, do they? So I guess we will have to. So let's go to the whiteboard. And let me move this thing out of the way. You can't see it, but it's a taskbar that they put in the white space, so it blocks white space for me. I've already moved you as far as I can, so then I'll take the whiteboard and move it as far to the left and up as I can to give me maximum white space to work with. That looks like about it. So here's the example 3. Somehow you knew that the magnitude of vector u is equal to 10. Now, frankly, in real life, how are you going to know that without knowing what the vector is? But we'll pretend. Magnitude of vector v, without knowing the components or anything, you just happen to know the magnitude, maybe you measured them, okay, is equal to 7, okay? And you happen to know somehow, without knowing what the vectors are, the angle between u and v. So the angle between u and v, vectors u and vector v, is pi-fourths. If any of you are really hung up on degrees, that would be 45 degrees. Okay, so it says find the dot product, u dot v. Magnitude of u, well, I'll write it down. Magnitude of u times the magnitude of v times the cosine of the angle in between. Okay, I'll put u and v here. Okay, so that will be 10 times 7 times pi-fourths. No, cosine of pi-fourths. What is cosine of pi-fourths? Any of you know? Square root of 2 over 2. Okay, I'm going to take this 2 and divide into 10 5 times. So that would be 35 times the square root of 2. Okay. I have a feeling they're going to evaluate this one too. Folks, I feel like I'm about ready to fall over. I don't know why. All term I've been trying to think of why I was so tired and making up reasons why I was tired. Well, I ate too fast, I did this, I did whatever. Okay, now I got it. Now I think I know. I've been anemic all term and didn't realize how badly anemic. 35 times the square root of 2. And they say that's right around 49 and a half. Okay. I'm going to put 49.5. I'm going to round it right there. That's the dot product between these two. Now, that kind of makes sense in the fact that the product of these two, 10 times 7 is 70, that is greater than that. That makes sense. The other thing is we know it's in the first quadrant because the dot product is positive. Okay, so those are the two pieces of information we know. Besides, I want to go to bed. Okay, goodness, I feel. Okay, they left it as 35 root 2. All the rest of them they've been giving the approximate answer to. This one they left 35 root 2, which is perfectly fine with me too. Okay, goodness gracious. feels so rotten. Let's go back to the slideshow. 11.3. Okay, and we'll resume the slideshow with here. That's what we were just using for example 3. Okay, now what we're talking about next are direction cosines. This is the top of page 773. Okay, here's the verbiage. In space, now this is talking about three-dimensional vectors in space, not the plane, in space. It is convenient to measure the direction in terms of the angles between the non-zero vector v and three unit vectors I, j, and k. Okay? So, if this is your vector v, now the trouble is you can't tell where v is pointing until you see something like this. See, when I first looked at that, I thought v was in the YZ plane. I said, well, that's not going to be a very interesting example. But then I say, no, it's not. It's coming out toward you here a little ways. So the angle between the I vector, the I unit vector in the x direction, and v, that is going to be angle alpha. So we'll get to this in a bit. The angle between j and vector v is beta, and the angle between k and vector v is gamma. Those are three angles given Greek symbols, which we usually use for angles. Those are the angles between that vector v and the standard unit vectors. Okay? Now, well, here's the deal. The angles alpha, beta, and gamma are the direction angles of that vector v. The cosine of alpha, the cosine of beta, and the cosine of gamma, those are all three angles, so you can take cosines of them, are then called the direction cosines of v, which is what we're naming this section, direction cosine. Now, v dot I, the vector v dotted with I, would be the magnitude of v times the magnitude of I, but guess what? Magnitude of I is 1. That's a unit vector. Okay, so forget about that. Times the cosine of that angle alpha. Okay? So, basically what we've got, that's the magnitude of v times the cosine of alpha. And that's what that dot product here is, v dot I. Magnitude of v times the cosine of theta. Now remember, the cosine of alpha. Remember, the cosine of any angle in the world is between -1 and 1. So if the alpha happens to be pi or 0, pi or pi, let's see. Yeah, pi or 0, then this will be a number that will be either minus the magnitude of v or positive the magnitude of v. Okay? Anything else, the cosine alpha is going to be between -1 and 1. So that means your magnitude of v will be reduced slightly to give you that dot product. If it's exactly 0, alpha is exactly 0 or pi, then v dot I will be exactly positive or negative magnitude of v. Okay? Now, what's more, v dot I would be v1, v2, v3 dotted with 1, 0, 0. That's what I is, right? And that just gives you v1. So magnitude of v times the cosine of alpha is just the component of vector v in the direction of the I vector. That's it. Okay? Now, it follows that the cosine of alpha which is this quantity here, is equal to V1 divided by magnitude of V. Okay, V1 is the magnitude of that component in the x direction divided by the magnitude of the vector. Okay, now, and that's going to be a number again between -1 and 1. I tell you, I'm about to lose it. I'm so sorry to have to do this so many times. It's almost all she wrote of that. Okay, by similar reasoning, with the vectors j and k, you have cosine alpha is v over magnitude of v, v1 over magnitude of v, cosine beta is v2 over magnitude of v, and cosine gamma is v3 over magnitude of v. Okay, now certainly the magnitude of v will never be less than v1, v2, or v3. It could, in certain circumstances, be exactly equal to them in value, absolute value, but they'll never be less. It'll always be more. So therefore, these are your components of well, I'm starting to give away where they go. Consequently, any non-zero vector v in space has the normalized, now here's that term again, normalized form. Now, when we say a vector is normal to a line or a plane, that means perpendicular. Okay. Here, when saying normalized, that means reduced to the unit vector. Normalized means you're reducing it to a comparative quantity of 1. So your unit vector in the direction of v is v divided by magnitude of v, which would be v1 over magnitude of vi plus v2 over magnitude of vj plus v3 over magnitude of vk. And if you took out this part, common factor 1 over vi, this would just give you the vector v1 I plus v2j plus v3k. So this would be basically cosine alpha I plus cosine beta j plus cosine gamma k. Okay, and because v over v, magnitude of v, is a unit vector, it follows that this sum, these are the components of that vector here, and since that is a unit vector, the sum of the squares of their components has to be 1. And that's what we got right here. Does that kind of make sense? Okay. All right, we've got a long way to go and I'm losing it. I think I'm going to have to go clear my head because I am getting so congested I can hardly breathe. So let me pause this. I hate to do this. I've been wasted so much time talking about things. Let me pause this and go clear my head. I'll be right back. And I think you've heard me say, goodness, I ate lunch. I must not have drunk enough water because I'm just really feeling clogged up. Well, I think what has happened is that, of course, when you eat, then more of your blood is taken digesting the food, you know, providing the energy to do that. And that's why you get sort of sleepy after big meals, you know. But now, being anemic, that has really complicated that big time. So I think that's what's been causing my issues that I've had periodically all term. I think that's part of it. Or at least that's my rendition. I don't know if this is right. All right, so here's example 4. And this is the bottom part of page 773, finding the correct direction angles. Now, if you haven't noticed this yet, time out just a moment here. Remember in the last section when we did vectors in the plane, okay, when we were talking about, and why this won't advance or retreat, I don't know, okay, when we were talking about a unit vector, what we had then was this. We had this expression here, and it was v1 I plus v2j over magnitude of v, and all like that. We didn't call them direction cosines then, we just said that was that. Now that we have three of these, that's where the term direction cosine. So this is how we define a unit vector in 3 space. It was pretty easy to define in 2 space. We didn't need this, but here we do have it here. So that's what we're up to here. Find the direction cosines and the angles for the vector and the direction angles, okay, for the vector. V1 is equal to 2i plus 3j plus 4k. Okay, now as we know before, v divided by magnitude of v is equal to 2 over, well, let's do the magnitude of v. V squared of 4 plus 9 plus 16. 4 plus 16 is 20, plus 9 would be 29. So this would be root 29. Okay. All right. And that would be in the I direction. Remember, I put hats over my unit vectors. That's just my little thing. Plus 3 over root 29 in the j direction, plus 4 over root 29 in the k direction. Okay. Now, as you also see, cosine alpha is equal to 2 over root 29. Cosine beta is equal to 3 over root 29. And cosine gamma, I can't write a gamma. Let me do it better than that. Let's see, where is it? There it is. I'm sorry. I got everything cleared momentarily. That's basically what a gamma looks like, is equal to 4 over root 29. Now, this is a very regular, predictable function. They all won't be that way. So let's find out what alpha is. That's the inverse cosine of 2 over root 29. Time for the handy dandy calculator again. Okay. Okay. All right. We do 2 divided by 29 square root equal, fairly small number, take the inverse cosine of it. And I get something that doesn't make sense. Oh, yeah, it does. Okay. I was forgetting. I'm in radian mode. Okay. This is about 1.19 radians. Okay. Now, 1 radian would be something about 50 some degrees. 1.19 is going to be an acute angle, but fairly close to 90 degrees, I think. I don't think it's much beyond that. Okay, we'll do the same thing here. 3 divided by root 29 wait, that did not work. I don't know what's wrong with it, but I've got fat fingers and very little keys. So let's clear that again. For some reason it's not clearing. I don't know why. So it's 3 divided by 29 square root, there we have it, equal, and that's 0.557. So, yeah, and then I need to do the inverse cosine of that, and that's 0.97. So beta is approximately equal to 0. I'm going to call it 98. Okay. Gamma, the cosine of gamma is 4 over root 29. So 4 divided by 29 square root equal, that's 0.74. Then take the inverse cosine of that, and you get about 0.73. So where is my pen? There it is. Gamma is approximately equal to, okay, what I keep forgetting is I've taken the inverse cosine. I don't think I have yet. Maybe I did. The brain isn't working well today. I'm going to have to start over. Okay, 4 divided by 29 square root equal, and then take the inverse cosine of that, and nothing happened. There we go. It's about 0.733, I believe. The problem here is okay. Oh, I'm on the wrong page. That's where the problem is. Oh, now this drives me nuts. Everything else they've done up till now has been in radians. And this example, they're getting 2 degrees. Now, why is that? I do not know. But let me go back and do it in degrees and see if we can get it. So we'll go to degree mode, and let's go back to 2 divided by root 29 equal, and then do an inverse cosine of that, and you get 68.2 degrees. So this will be approximately, theta is approximately 68.2 degrees. Okay. Beta, on the other hand, would be 3 divided by root 29 equal, no, what did I do? Oh yeah, and then do an inverse cosine of it. I just can't keep my head about me. Beta is approximately equal to 56. I'm just going to leave it about 56 degrees. And gamma is approximately equal to, I could have just done this up there, 4 divided by root 29 equal, and do an inverse cosine of that, and I get about 42 degrees. Okay, now, is there something magical about these angles? Not really, okay? They're not. They don't add to any special thing. I don't think. No. So there's nothing special in per se about them, but what they do, notice that, of course, because as the angle is increasing in the first quadrant, which all these are, your values are decreasing, and we saw that, or when the values are increasing, the angles are decreasing. So we do see that, and that makes sense. Okay. Now, they did 68.2, 56, they said 0.1, and 42.0. That's basically what I got. And if they did the sum of the squares of those, that's the last thing they said here. Find the direction cosines, those are they. Okay. Find the angles, those are they. And these were almost in radians, but until I realized they were giving them in degrees. And then the last thing it says, show that the cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. So we can do that. It just seems a little nuts too, because this is cosine. You square it, you get 4 over 29. You square that and you get 9 over 29. You square this and you get 16 over 29. And 16 plus 4 is 20 plus 9 is 29 over 29, and that's 1. So that seemed like to be almost a crazy thing to ask you to do, but maybe they wanted you to plug these numbers in and do the cosine of this squared plus the cosine of that squared plus the cosine of that squared, and see what it came out with. And I bet you'd have gotten very, very close to 1. All right. I can't believe it, I'm losing it again. Caffeine went for a little bit, but not long enough. And there's not enough there to last me much longer. Let me see if water will help. Okay. Let me erase what I did. And let's see how they do it. Because the magnitude is root 29, we got it. You can write the following, that the cosine of alpha is 2 over root 29, which we did. Cosine of beta, and that's about 68.2 degrees. Okay. Cosine of beta was 3 over root 29, making beta approximately 56.1 degrees. And gamma, cosine of gamma was 4 over root 29, which made gamma about 42 degrees. Notice how they decrease, just exactly what we did before. Now, what they're doing now, they're saying cosine squared alpha plus cosine squared beta plus cosine squared gamma. What they're doing is doing this squared, which is 4 over 29 plus 9 over 29 plus 16 over 29. That's exactly what they've got here. Add the 3 numerators together and you get 29 over 29 equal 1. Okay? So, therefore, this is a unit vector, this right here. Although ever show, that's not a unit vector, but the unit vector that you get from this times I plus that times j plus this times k is equal to a unit vector. And these are the components of it, the cosines. Okay. Okay. I think we beat that about into the ground. Let's just see where we are in the text. Goodness gracious. 9 minutes. I think I can do it. All right. We are ready for page 774, projections and vector components. Okay. This follows pretty closely what we were just doing. You've already seen applications in which 2 vectors are added to produce a resultant vector. Yeah, we did that a while back. We did it mostly in 2 space. I don't know if we've done much of it in 3 space, but it works the same way. Many applications in physics and engineering pose the reverse problems, decomposing a vector into the sum of 2 vector components. Okay, And these aren't always your x, y, z components or x and y components. This following physical example enables you to see the usefulness of this procedure. And this is a classic problem in physics. Let's consider a boat on an inclined ramp, okay, shown here. Now, the interesting thing is they didn't say anything about the angle of the ramp. Usually they do, but you don't have to. They're just doing this figuratively. Now, the force due to gravity, guess what? Always points straight down. That is your force due to gravity, also called the weight. Okay? And the shallower the angle like this, the greater the component of that weight perpendicular to the ramp. That's your W2. The component of that weight parallel to the ramp is called W1. Okay? Those two add to be vector F. Okay? They're the component vectors of it. Not the IJK component vectors, but the parallel and perpendicular component vectors of F. Now, what they didn't show you here, and I think it's well worth showing, is that if you did, which most of the time I think you will, know the angle of the ramp here, this angle right here, let's call it theta for lack of anything else to do, because that's this angle right here would be the complement of theta, because I can't stand that. This right here would be the complement of theta. It keeps, I draw it and then it, okay, because they make up this little right triangle here. Well, this is also the right triangle that you have here. And so this is a right angle here too. Now, because this here is also a right angle, we know that this angle here and this angle here are complementary to each other. We also know that this angle here and this angle here are equal to each other. Okay? Which then means this angle here and this angle have to be complementary, but let's see if I can get all this straightened out here. This angle and that angle are the same, but okay, here it is. Here's another right triangle you could do right here. I don't have it written up far enough. That says these two angles here are complementary. Well, if this one's complementary to that, these are complementary, so these two angles are the same. So that means that this angle over here is the same as your boat angle, the ramp angle here. This is the ramp angle there. Okay? So that took a long time of explaining, but that's what you get from this, and that's always going to be the case. Okay, now I think that sets us up for example. No, it doesn't. Okay, now force F, the total weight of that boat, is the weight, let's see, I can't remember which they call it, weight parallel to the ramp plus the weight perpendicular to the ramp. Now this has another name for it, by the way. This is called the normal force. Well, not quite the normal force. It's the same as the normal force, and remember, normal means perpendicular to the ramp. So if you were to draw, and I can't draw it well, I'll try to extend this upward. That's supposed to be a straight line. This is called the normal force. You're going to get into this in physics. That's the force perpendicular to the plane. That's the force that the plane is holding the boat up with, and the only component of the weight that's pulling it down the plane is this one. That means the only component that you have here that you have to exert to pull the boat out of the water is something in excess of this, because most of that weight is on the plane, not on what you're having to pull, and therefore a shallower bank is going to be less force that you have to exert to pull it up the ramp. Okay, that's carrying on. The forces W1, that's parallel to the plane, W2 perpendicular to the plane, help you analyze the effect of gravity on the boat. For example, W1 indicates the force necessary to keep the boat from rolling down the ramp, whereas W2 indicates the force that the tires must withstand perpendicular to the ramp. Okay? So here are your definitions of projection and vector components. Let U and V be non-zero vectors. Good choice. Moreover, let U equal W1 plus W2. Now, whatever that is, those are two components of your U vector. Okay? We don't know with respect to what. It could be a ramp or whatever. Where W1 is parallel to this vector V here, and W2 is orthogonal to V. So U and V are two non-zero vectors. U is broken into components. One of those components is parallel to V, one is perpendicular to V. Okay? Now, W1 is called the projection of U onto V. Okay? So here's the vector U, here's the vector V. Okay? If you were to do two components here, W1 parallel to V and W2 perpendicular to V, that W1 would be projection of U onto V. Now, think of this with projection. Imagine you had a light somewhere up this way. The light was, oh, I'm sorry, I can't write on the screen there. The light was somewhere up here, directly overhead. Well, I can't, oh, there it is. Directly overhead here. And the light is shining down on this vector U. And this is perpendicular to V, okay? Then this is the projection, the shadow vector U would make in the direction of V. In this case, V actually is shorter than the projection W1. Now, if you had a light way over here to the side, shining on vector U this way, the shadow of vector U onto, say, the y-axis here, the W2 axis here, that would be the magnitude W2. Okay. So that's why you can think of projection, the part that would be shadowed by a light directly overhead. Okay. W1 is the projection of U onto V, and the vector component of U along V, denoted by W1. W1 is equal to projection of V onto U. W1 is projection of, of U onto V. Okay, I said it backwards. W2 is then U minus W1, because you see these two, W1 and W2, add up to be V, so therefore W2 has to be U minus W1. Okay, that's called the vector component orthogonal to V, perpendicular to V, and that's the component of U perpendicular to V. Okay, now what if theta was obtuse here? Okay, component of U onto V would be a minus. W1 would be in the opposite direction of V. W2 would still be upward. Okay, that's a component of U perpendicular to the V vector. Okay, and I think that ran us out of time. Sorry about that. We're ready to do example 5. So that's where we'll pick up next time. Okay, example 5. Okay, we made good progress. My interruptions are bad. If I hadn't had those, I think we would have finished. Homework exercises in 11.3 would be any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 17, they're all at Calc Chat. 13's at Calc View. 19 is both at Calc Chat and Calc View. 21 through 25 are all at Calc Chat. 27 or 29 are both at Calc Chat. 31 through 35 are all at Calc Chat. 31's at Calc View. And let's hold off 37 until we get the next examples done. And then we'll finish with 11.3 and move into 11.4 next time. Any questions? All right. Okay, if there are none, thanks for being here today. I'm sorry I wasn't totally here today. Goodness, I feel so tired. But last bit of Coke I think helps some. Gonna end the meeting here unless there are any problems or concerns or questions. Any? Yeah, what you got? Okay. All right, well, thank you. I appreciate that too, but wipe it off. No, I'm just kidding. Okay, no, I thank you for your sentiment. I think I know what you're talking about because this isn't particularly easy right now, so thank you for acknowledging that. Take care, folks. Be safe. We'll see you on Wednesday. Take care. Bye-bye.